Alright, in this video I'm going to be giving a intro to support vector machines, or also abbreviated as SVMs. Okay, so let's first talk about, in general, what a support vector machine is. A support vector machine is a machine learning model that learns from data, and it learns from data how to classify examples in a data set into k different classes, where k is some number 2, 3, 4, so on. Now, that was a very abstract definition. Let's start a little more concretely. So what do I mean by classification? All right, so what I mean by classification is, say we have an example in our data set, and this data set has two features, x1 and x2, right? The goal of a support vector machine, or for any machine learning model that's doing classification, is to take this example, x1, x2, and put it into one of these classes, right? It could fall into class 1, can fall in the class 1, or you can put it in the class 2, or you can put it in the class K. And that's the goal of the support vector machine, and that's what I mean by classification. And so also every example in a data set is going to have its features, and it's going to have the class that it belongs to in the data set. All right, so now I'm going to give a concrete example of what I mean by classification. So let's say we have a data set. Okay, so let's say we have a data set X where we have two features, where this feature is x1 and this feature is x2. Now so in this data set we have 1, 2, 3, 4, 5, 6 examples. And for each of the examples we have a classification of either 0 or 1. So example 1 here has a classification of 0. Example 2 has a classification of 0. Example 5 here has a classification of 1. So there's two classes. All right, so for this data set, let's say x1, the first feature here, and x2, the second feature here, represents the leaf width. X1 represents the leaf width, and x2 represents the stem lengths of a flower that we measured, right? And let's say our classes, class 0 and class 1, stand for, class 0 standing for Iris setosa, a particular species of iris flower, and class 1 stands for Iris virginica, another particular species of iris flower. And so for an iris flower, you might have taken a measurement of the stem lengths, like so for this flower, and this stem length would be x2, the first feature, and then we would choose one of the leaves on the iris flower that we measured to generate our data set, and we would measure its width, I guess the maximum width of the leaf, and you would have that feature be x1. And so in this data set, we did that for 1, 2, 3, 4, 5, 6 examples, or 6 flowers, and that generated our data set, just to make this more concrete. So the goal of our support vector machine, or really any classification machine learning model, is to use the x1 and x2 features of a flower, so this leaf width and stem length, using those predict the species or class 1 or 0 of the flower. Right, that's what we're trying to do. So give me x1 and x2, and I want to be able to predict what the flower species is. Is it Iris setosa or is it Iris virginica? So take in the X1, X2 features and give out Iris setosa or Iris virginica. All right, so here I redrew the data set of our that we had in the previous page, and the class vector, which gives the class for each of the examples in our data set. Now, what we're going to do is we're going to take this data set and we're going to plot it, and we're going to use zeros. Right, in the data set, we're going to use zeros for Iris setosa. Right, that's if a point in the data in the plot of the data set is a 0, then it's an Iris setosa flower, and we're going to use 1s for Iris virginica flower. Right, so I'm going to plot the data set, and each point that is an Iris setosa flower is going to be plotted with a 0, and each point that is a Iris virginica flower is going to be plotted with a 1. All right, so here I plotted the data set, and I plotted, as I said, 1s for Iris virginica. So all these purple points in the data that we said that we plotted are the Iris virginica flowers, and I plotted the 0s for the Iris setosa flowers. So all these 0s here, or these light blue data points, are all the Iris setosa flowers. Now, what could we do to classify ones? How can we tell that Iris, one of these points is Iris virginica? Like if I had a new point, say it was here, how could I use this data set of blue data points and purple data points to determine if this new X point is going to be a Iris setosa or a Iris virginica flower? Well, what we could do is we can draw a line. We can draw a line to divide the two classes. Right, we have two classes, Iris setosa and Iris virginica. We can draw a line through this leaf width and stem lengths feature space to divide the two classes. And here, this line would probably be one of the best lines you could draw, but there's many other lines that actually satisfy this. So we can use this blue line that I drew, right, to separate the classes, so that every data point that falls to the right of this line is classified as Iris virginica, right, because these are where all the purple points are. And every point that's to the left of this line, will be classified as Iris setosa, since that's where all the Iris setosa flowers are, or the data points are in this data set. And so this X here that I plotted would be classified in this case as an Iris setosa flower. Now, mathematically, a line we usually describe with y equals mx plus b, a linear line in a 2D space. We usually describe with this equation where m is the slope and b is the y-intercept. And x is kind of your input, or your input variable, and y is your output variable. But there's a problem with this particular line here, right? Here we have x2, which is an input or a feature, and here we have x1, which is an input or a feature, right? But here in this equation, y is an output, right? That's kind of our prediction. But this line is not, there's no y, there's no output, so y equals mx plus b doesn't quite work. Or the general equation would work, but this doesn't predict the output. So instead, what we have to do is we have to use another equation, which is, well, we can rearrange this equation, but you can use another equation, which would be W transpose plus B, W transpose times X of I plus B is equal to 0. Here, W transpose, right, are two parameters, W1 and W2, and this transpose makes it a row vector. And this W transpose is essentially the slope of our line. And B is still the y-intercept. But here we have W transpose X of I, where X of I is just it's an example in our data set. And this equation, W transpose X of I plus B is equal to 0, describes our line. Okay, it's worth spending more time on this line equation because you might not have seen this before, and you might have, most likely you've seen y equals mx plus b describe a line, but this might be a little foreign to you if you've never taken a linear algebra or a vector calculus class or anything like that. So effectively here, W transpose is a column vector, W1, W2, and X of I is a row vector. I'm sorry, W1 is a row vector. W transpose is a row vector, and X of I is a column vector. Right? And we take the dot product between these two vectors, and we add B, and we set that equal to 0, so that this is rewritten as W1 times X1 plus W2 times X2 plus B is equal to 0. Right, and this equation does describe a line. And you can actually rearrange this into a y equals mx plus b equation. What you have to do is you subtract by W1, X1 on both sides, and you end up getting y and b on both sides, and you end up getting negative W1 X1 minus b, right? And then you divide by W2 on both sides, and you get X2, right, is equal to negative W1 divided by W2 X1 minus b over W2. And this is kind of a y equals this negative W1 over W2 is your m, and you have X1, which is your x, and you have plus b, which is this negative b over W2. And so this basically does describe a line, and the signs don't really matter here because W1 and W2 can be negative, so these signs don't matter too much because they'll just change if W1 was negative. But this equation, I just showed that it does describe a line just like y equals mx plus b, so you can use it to separate the two classes in our original data set here, right? This line here would be sum W transpose times X of I plus B is equal to 0. That's what we describe this blue line here that separates the purple data points or the Iris Virginica data points from the zero data points or the Iris Setosa data points. All right, so now I'm going to describe how we actually make the classification mathematically. What I said earlier was if you're to the right of this line, then you're classified as a 1 or a Iris virginica, right? And if you're to the left of this line, then you're classified as a Iris setosa or as a class 0, right? So if I had a data point here, it would be classified as Iris setosa, and if I had a data point here, it would be classified as Iris virginica, right? But how do we make that actually mathematically? I mean, how do you take in x1 and x2, right, and then put it through some process, and then get out, the 1 or 0 class. Right? How do we do this mathematically? So that we can actually, program this rule of being to the left of the line and being to the right of the line classification rule. So we can program that into like a Python program or something. All right, so I said earlier is how do we mathematically determine if a point x1, x2 is to the left of the line or if it's to the right of the line. How do we do that? Well, I think it'll help if you understand this definition of the line. So W transpose x of I plus B, right? W transpose x of I plus B equal to 0 tells us that the line is defined by all the x of i's, right? All the x1 comma x2 values on this line. So this value, this value, this value, that have a W transpose times x of I plus B equal to 0, right? So it's equal to 0. So imagine if you had like 1.0 and 2.0 as your W1 and your W2, and you had x1 and x2 equal to -2 and +1, right? And let's say your B is just equal to 0 in this case. Right, so that W1 times, W transpose times x of I plus B, that would equal 1 times -2, 1 times -2, plus 2 times +1, plus 0 from the B, and that would give you -2 plus 2, which would give you 0. So this point would be on your line. Now, if you nudged x1 just a little bit, right, if you nudge x1 just a little bit, so x1 is at -2, right, so x1 is negative. So if you nudge x1 just a little bit, right, say you made it -2.1, then you would have -2.1 times 1 plus 2 times 1 plus 0, right? This would equal now our W transpose x of I plus B. And that would give us a, this would give us a -0.1. So if you nudge x1 just a little bit, that would give you a negative value for W transpose x of I plus B. Now, if you nudged x of 2 just a little bit, right? So let's say we went from +1 to 1.1, then your W transpose x of I plus B would equal -2 times 1 plus 2 times the new x1, which would be 1.1, plus 0. And so this would be -2 times 2.2, so this would be equal to positive 0.2. Right, so if you nudge a little bit in the x1 direction, then you end up with a negative number. And if you nudge a little bit in the x2 direction, you end up with a positive number. right? And so what you can deduce from this is that if you're on the, say, the left side of the line, W transpose X of I plus B is less than 0, right? Because if you nudge, if you're on the line and you nudge, say, X1 a little bit, then maybe you end up, like if you're on the line, you nudge X1 a little bit, maybe you'll end up, being more negative. And you could also say if your W transpose X of I plus B is greater than 0, right? If your W transpose X of I plus B is greater than 0, so that means if you nudge, maybe, you're on the line and you nudge X2 maybe down a little bit, and you end up, on the right side of the line, so now you're positive, you increase your W transpose X of I plus B a little bit more, and you're on the right of the line. So this rule, where if your W transpose X of I plus B is greater than 0, then maybe you're on the right side. And if your W transpose X of I plus B is less than 0, then you're on the left side. So this line basically divides, this line here, and this blue line, divides all the negative x1, x2 values from all the positive x1, x2 values. And so by using this rule, we can take in a x1, x2 point, right? And we can say, if W transpose X of I plus B is greater than 0, then we can say it's in class 0. And if W transpose X of I plus B is less than 0, then it's in class 1, or on the left side of the line. And from here, you can get out the classification of your point, of your data point. And that's how you can encode the rule, where if you're on the left side of the line, you classify it as a Iris setosa, and if you're on the right side of the line, you classify it as Iris virginica. You can use this inequality, or this if statement with this inequality, to do that. All right, I think I'm going to finish up with that as the intro to support vector machines. Next time, I'll try to describe more of the mathematics, fundamental mathematics behind it. And thank you.